Good morning, everybody. My name is Mauricio Gomez, and today I'm going to talk about the scattered storage assignment problem. As you might know, e-commerce has been growing considerably in recent years. It's such an important increase in the sales in this type of business that by 2021 is expected a minimum increase about 17%, and even more by 2022, which is going to be around 35%. All of this screen on sales in this type of business has produced new challenges for the companies who are working in this topic. So for example, nowadays, customers are demanding more variety of items, but in small quantities. Also, those customers are demanding different amount of items according to the different months in the year. As well, the customers are expecting better lead times, which means that the companies that are working in this business need to attend the demand of those customers as soon as possible, since the product is produced in the factory until that product can be delivered until its final destination. During supply chains process, there are many challenges that the companies need to face daily, but for the case of this research, we are going to focus only on the activities that happen in the warehouse. Normally, companies are storing their products in the traditional way. The traditional way is when one family of items can be stored close by. For example, in one aisle or 2 or 3 aisles close by. But for the case of this research, instead of to allocate the items in the traditional way, we are going to allocate the items through the different position in the warehouse, as you can see it in the picture. So the idea behind of this method is that an unproductive working time can be reduced because of that. Because also there is more chances to find an item close by. Suppose there is one picker who needs to go to collect the items to meet the demand of one specific order. So the idea is that that picker can identify those items in the same aisle or perhaps in 2 aisles. So with that process, the working times or the routing time in the warehouse can be reduced. This problem is a little bit new. So far, only one mathematical model has been proposed. It's the one proposed by Wedner and Boysen in 2017. Basically, they developed an optimization model to minimize distances between some measuring points located across to the warehouse with some specific positions. But for the case of the research, we are going to minimize the distances between positions of the same order. The main characteristics of these problems are the ones related, for example, with the capacity of the positions for the different products. Each pair of distances between 2 positions are knowns, and each ordered item must be retrieved from a single position. That means, for example, if one specific customer is demanding 3 units for a specific item, those 3 units must be retrieved from a single position instead of 2 or 3. Those are the most important parameters that we are going to use to tackle this problem. Now, look this graph. Suppose that one order is demanding 5 type of items. So those type of items need at least 5 type of positions. So suppose these 5 nodes are the 5 positions that the specific order is demanding. So the idea is to try to minimize the distances between each pair of positions in that specific order. For example, between position 1 and position 5, position 4, position 3, and position 2, and so on. So that is the idea with the case of this research, and we decided to call that distance as the sum of the pairwise distances between positions of the same order. If you see that as well, this graph looks similar to a complete graph. If you remember the graph theory. So this is an important issue that we are going to use to create some valid inequalities in the next stage of this research. So in the end, we want to minimize the SPD for the total order that we need to solve in each instance. The formulation, the basically formulation for this problem is the one that you can see in this slide. Basically, this is a binary formulation because all the variables are binary. The main constraints are related. For example, we need to respect the capacity of each single position. In each position, only one type of product can be assigned. All orders items must be assigned through the different positions. And in the end, we want to minimize the SPD for the whole orders. This formulation was difficult to try to solve by using the commercial solvers like Simplex or Gurobi. So for that reason, we decided to create a new procedure to tackle it in a better way, this problem. If you see the constraint number 6, the variables who are in blue, X and V, are the variables that we are going to relax to solve this problem by using linear relaxation, and then we are going to apply some valid inequalities to stretch the formulation and to eliminate some fractional results. So in order to do that, we developed two groups of valid inequalities. The first group are the ones that come from to the graph theory. In graph theory, as you remember, there are many properties that we can use for this problem. To be more specific, the graph that I showed you previously is an example on a complete graph. So for the case of the research, it's similar because we have 5 positions, for example, for one specific order, and we need to connect, or we need to minimize the distances between the connection of all of those 5 positions. So the idea is that we can force to those variables to take some integer values. So because we know in advance how many edges must be in each specific graph or in each specific order, we can force to some variables to take some integer values instead of to fractional. But after to apply this procedure, as you can see in the constraint number, from constraint number 7 until constraint number 10, we realize that we still have some fractional values in some of the variables. So in order to tackle this second part of the problem, we decided to create another group of valid inequalities. If you remember the NAPSA problem, the NAPSA problem works a little bit similar to this problem because in the NAPSA problem you have a NAPSA and you need to assign some items into that NAPSA in order to maximize an objective function. For the case of this research is a bit similar because we have a position and we need to define what type of item to assign there and also how many units of that specific item to assign in that specific position. So the valid inequalities that we propose for this problem are the ones developed by Lecture and Soil in 2019. And the main idea behind of that is that we need to create a minimal cover. The minimal cover is suppose we sort the items that we are going to assign in that specific position from the smallest one until the largest one. And then we assign each item until we can fill the total capacity of that specific position. Once the position is filled, we account the number of items we were able to assign there, and that number is the minimal cover, as you can see here in this part in the constraint 11, and this part in the constraints 12. So the items that were able to assign in that specific position, that are the items included in the minimal cover, are the ones that you can see here in the second part of the constraint. But the other items that were not possible to assign in that minimal cover, we are going to affect by a parameter called alpha. And that parameter is calculated according to the weights of those specific orders. So in the end, the constraints number 12 and the ones proposed for graph theory are the constraints or valid inequalities that we are going to use in our linear relaxation to avoid to have fractional values and also to improve the objective function that we want to minimize for this problem. So to analyze the performance of our formulations, we create 24 instances. Each instance contains information about the number of positions, number of orders, and type of products, and the total demand for each instance. So the first group of results that we want to show you are the theoretical results. The results are presenting, for example, the SPD in each type of instance and also the gap. The gap is how close each model was to the optimal solution. The first two columns are the results that were provided by the initial formulation without any valid inequalities, and the second columns are the results provided by the second formulation with valid inequalities. If we go to the end of the road, the results showed us that the formulation with valid inequalities was better in total, in average, and also the gap obtained by the second model was better. So in total, we were 38% close to the optimal in average in comparison with the first model without any valid inequality that was 85% close to the optimal. So that means that the formulation with valid inequalities was much better than the initial one. And also we were able to solve almost the whole instances except for the 21 that was a little bit difficult. We have to notice as well that each instance was performed in a maximum 1 hour of computational time. After that, each instances, we decided to stop. The second group of the results, or the second part of the results, are the ones of the applied results. In this case, we want to present, or what are the results in comparison with other type of storage allocation policies. So for example, the first idea is to compare our scattered storage with traditional storage. And also we want to compare scattered storage by using optimization models, and also compare those results with scattered storage by using random assignments, as you can see here. Random storage assignment and traditional storage assignment. So in the end, if we see the results, our scattered storage was much better than the random storage assignment, and also than traditional storage assignment. Random storage assignments, to be more specific, is the scattered storage method that some companies are using nowadays, but they don't use any optimization model. They normally apply random assignments in order to get some scatterage in their warehouses. So in the end here as well, we were able to prove that our formulation with scattered storage using mathematical formulations was better than traditional or random assignments. If we want to see it with more detail the results, suppose in this graph or in this picture, the first part of the picture, we have some specific traditional warehouse where the products of the same family are stored close by. For example, the yellow ones are together, the red ones are together, the blue ones are together, the white ones are together, and so on. So in the second part are the products allocated in a scattered way. So suppose, for example, the red one is in the first aisle, the second red one is in the second aisle, and the last red one is in the third aisle, and so on. So that is the idea behind the scattered storage. So if we analyze one specific order, suppose that we have the order number 10, and that order is demanding 6 type of units or products. So suppose that that order is demanding a yellow one red one blue one green one, and so on. So in the first case, the picker will have to go to the first aisle, second aisle, and the third aisle in order to collect the whole items that specific order needed. And the total SPD, or the total distance, in that case will be 116. But what happened with the second case? In the case of the scattered storage, the picker only have to go to the second aisle. So in that case, the picker was able to get or to identify the whole items in the same aisle. And in that case, the total distance or the total SPD was only 19. So the comparison between both numbers are really, really significant for the case of this research. Now, suppose the second, this is another example, other order. So in the first case, the picker has to visit 2 aisles in order to collect the whole items. But in the second case, when scattered storage is the policy, the picker only has to go to the first aisle in order to collect the whole items. And the total distances are 28 in comparison to 10. Also more than 60 or 70% better in the scattered weight in comparison with traditional storage allocation. So as a conclusions, we can say that our scattered storage method is a really useful method to apply for some specific business. To be more clear, for this type of storage work quite better for e-commerce. Also, we can conclude that our formulation with valid inequalities was 14% better than the initial formulation without any valid inequalities. In general, scattered storage was 24% better than random storage allocation, and 46% better than traditional storage allocation. That is an important number that we need to take into account. We have to say that exact methods are useful to solve small instances and some of the medium instances, but for larger instances, it's quite difficult to get at least some feasible solutions. So for that reason, we are proposing for future research to develop some heuristics or meta-heuristics to tackle it in a better way this specific problem. Also, to become more realistic this problem, we are interested in applying more elements to this problem. For example, the concept of the depot. You know that in a warehouse, it's really important, the depot. So we wondered what would be the results if we decided to include the depot. Perhaps in the way that we assign the items should be different. Also, the blocking effect. The blocking effect is according to the way that we assign the items in the warehouse, perhaps we are generating some blocking between the different pickers. So that is one of the questions that we should try to answer for future research. So that's it, and I hope you have liked this presentation. Thank you very much.